Hey, Dr. Clark here as always, and in this video we're going to learn how to do surface integrals. Let's get started. So surface integrals are kind of an interesting idea in calculus. It's really the idea of line integrals upgraded to two-dimensional. So a line integral, remember we had some function, we had some curve, and maybe that function gave you the density of that thin wire, and as you integrated the density over the wire, you got the mass, right? Well, now imagine you have a surface, so some two-dimensional surface, and the function maybe gives you the density, right? And if you integrate the density over that whole surface, then you could get the mass of that surface, something like that. So it's really taking the idea of line integral, upgrading it to a surface. And mathematically, the way this really happens is we had parameterized the line or the curve with r, the parameterizing function, and t went from t0 to t1. And then the velocity of that r prime, made into a magnitude, gave you the length, right? So ds, that length, piece of length, was really the velocity times time. That gave you that length. So what we're going to do is something similar where we have a function and then we have a patch of surface, and it's going to turn out that measuring the area of a patch of surface is really the area below the surface, the shadow, a little rectangle underneath, times the stretch factor. Remember, the velocity of the curve gave you the stretch factor, how much a little dt got stretched into two dimensions. Well, this quantity will really just give you the stretch factor for a small rectangle being stretched into a surface. Okay? And the way this works is you can either have the surface be given by some function z equals g of xy, right? And so that position function is really a vector xy, g of xy. Or you can have the surface be something like a sphere or a cylinder or a cone, which doesn't necessarily get written nicely as a graph, g of xy, and then you have to parameterize it. And what I'm going to do is only look at option 1 here. I'm just going to look at surfaces that are given via a function z equals g of xy. There are ways to do this, but I'm going to just focus on this concept right here. Okay? And so what's going to happen then is a surface integral. For example, if you wanted surface area, you could just integrate the one function with respect to that surface patch, and that'll give you the total surface area. If you wanted to do that, though, you'd want to switch it. You'd want to look down underneath the surface, dA, the shadow of the region, right? And then you just have to know what that stretch factor is. But we saw a minute ago what is that stretch factor? It's just the square root quantity. And what's going on is if you have a little patch of rectangle, that gets stretched into a patch of surface, and it turns out the x gets stretched by a certain amount, the y gets stretched by a certain amount, and the total stretch factor is equal to 1 plus the x derivative squared plus the y derivative squared. And this should look very, very similar to this. When you did the magnitude here, it was the same, except it was 1 plus gx squared, basically. So it's that same concept, it's just for a surface. So the definition then of a surface integral, if you want to do a function integrated along a surface, you look at the shadow under the surface on the xy plane, and you multiply dA by the stretch factor, and then you multiply that by whatever the function takes on. Setting f equal to 1 gives you the surface area, but it could give you a mass or something like that if f was some other function. And it should look, it's very similar to that line integral, right? Where, what was the arc length or whatever, had a very similar format. Right? You can kind of see that there. All right. So in the next video, I'll do a couple examples walking you through how to do these problems, and then we'll see you then.